Go ahead.
Okay. So can I start?
Sure, sure.
Okay. So today the presentation is my presentation is about a general lower bound for the chromatic number. Uh, so mainly what we are trying to do here uh, is to determine general lower bounds of the chromatic number of a given graph G. So I mean for any graph G. So the way we proceed with this is first we introduce some simplicial complexes associated with the graph. First, we introduce something called the Bot's complex B of G, and then using this, we derive a lower bound of chi of G in terms of its index. Index of B of G actually. It should be index of B of G. So chi of G is greater than or equal to index of B of G plus 2. We derive this thing. Then we construct something called the neighborhood complex of G, and also some simplicial set to complex called L of G. And using both of this, we prove a second lower bound. Chi of G is greater than or equal to K plus 3, where K is the connectedness of N of G as a topological space. The connectedness, as we mentioned in Nurshida's presentation. Uh, also, we also mentioned one application, the generalized Mycielski graphs. So Mycielski graphs are constructions that were invented to construct triangle-free graphs of arbitrary large chromatic number. So if we have a graph G, we have a triangle-free graph G, we can construct something called M2G
Deepak,
with
just a
from.
small suggestion. I think your mic is very near to your mouth.
Okay.
Yeah.
Yeah. So given a graph G, we can construct a graph M2G such that the chromatic number of M2G is one greater than that of G. Uh, so yeah, we first start with some of the definitions. Mm, So a common neighborhood of a subset of V of G, the vector set of G, is the vertices of V of G such that uh, V belongs to V of G such that AV, where A is in A. Basically, V is a common neighbor of every vertex of A. That is what this means. So Cn of A is defined as all the vertices which is adjacent to all of A. And now Cn of A is disjoint from A. That is easy to see because we cannot, if you have a intersection, then that vertex should be adjacent to itself. But this is not possible in a graph. Uh, Now we define what a graph homomorphism is. A graph homomorphism is a map F from vector set of G to vector set of H such that edges are taken to edges. We can see that a graph G can be properly colored by M colors if and only if there is a graph homomorphism from G to Km. So we start with the Bot's complex construction. So given a graph G, we can construct a simplicial set to complex V of G. The vertex set of it is V of G disjoint union V of G. So we take two copies of V of G and disjoint union them. And the simplicities of V of G are given by A1 disjoint union A2, which is non-empty, such that A1 and A2 are contained in V of G. Their intersection is empty, and the bipartite graphs induced from A1 and A2 is complete, and their neighborhood of both A1 and A2 are both non-empty. Uh, so basically, we can see that the simplicities of B of G are the non-empty bipartite subgraphs of G, or one of the AIs is empty and the other is non-empty with a common neighborhood. Okay. So now we define the simplicial set to action on B of G. So simply the set to action is just given by interchanging the corresponding vertices on these two copies. So V1 goes to V2 and V2 goes to V1. Uh, Now we can see that this set to action is free because given any if nu of x is equal to x, then that just means that nu of s intersection s is non-empty, where s is the simplex containing that point x. So we can show that for any simplets, the intersection is empty because nu of A1 union A2 intersection this thing is this thing, which is empty because of A1 intersection A2 is equal to 5. We also we also mentioned that B is a functor from category of graphs to category of simplicial Z2 complexes with simplicial Z2 maps. The given a graph homomorphism F, the B of F is defined as the obvious way, like Vj goes to F of E comma J. This gives us a simplicial Z2 map. Thus, this defines a functor. By extending this with the geometric realization functor, we can get a functor from category of graphs to category of set2 spaces. In particular, whenever G is M colorable, there is a set2 map of B of G into B of Km, because just by taking the functor on the F from G to Km, as we had mentioned here, if it is M colorable, then there is a map from G to Km, so we can apply B on it and get a Z2 map from B of G to B of Km. Okay, so we what we intend to do is, like, we have to prove this inequality here. So for that we mentioned a lemma here. The lemma says that index of B of Km is less than or equal to M minus 2. We just give a rough sketch of this proof. So it can be proved that B of Km is isomorphic to the boundary complex of M-dimensional closed polytope with two antipodal faces removed. This can then be set to mapped into SM minus 2. I'm not giving the actual maps here. I'm just giving like a rough idea of what the proof is. Now using this lemma, what we can do is we can prove this inequality. So we know that B of G maps into B of Km, Z2 maps into B of Km. So that just means that index of B of G is less than or equal to index of B of Km. So using this inequality, we can get the index of B of G is less than or equal to M minus 2 when G is M colorable. So M here means that M here is just chi of G. So what we get is index of B of G is less than or equal to chi of G minus 2, which gives us this inequality here. So we have proved the first inequality that we mentioned in the overview, this one. Now we try to prove this thing. So for that, we proceed on to the neighborhood complex. So the neighborhood complex is another simplicial complex. The vertex set is V of G itself, and the simplices are given by the subsets of V of G, non-empty subsets of V of G, such that its common neighborhood is non-empty. So here is an example, a graph G and its neighborhood complex is shown here. Okay, so on to the second inequality that we showed. So again, we mentioned a lemma here. So for every graph G, we can associate a simplicial set to complex L of G, such that L of G is a deformation retract of N of G, and L of G set 2 maps into B of G. So the construction of L of G, we mentioned it in the next section. We did not do it here, but using this lemma, we can prove the second inequality that we need. So what we do is, in a neighborhood, so if N of G is K connected, then L of G is K connected as well, because it's a deformation retract of N of G. So what we get is index of L of G is greater than or equal to K plus 1 due to the properties of index. So index from this thing, we get index of B of G is greater than or equal to index of L of G. So using this 2, we get index of B of G plus 2 is greater than or equal to K plus 1 plus 2, which is K plus 3. So chi of G is greater than or equal to K plus 3. This part comes from the previous inequality that we proved here. Chi of G is greater than index of B of G plus 2. Yeah. So what we get is, we get a lower bound of chi of G in terms of the connectedness of N of G. Okay. So now we proceed on to the construction of LFG that we mentioned in the previous section. So we construct LFG as a subcomplex of subdivision of NFG, which we denote by N1. Since the subdivision is geometric relation of subdivision is homeomorphic to that of this thing, we get that LFG can be represented as a subspace of NFG. So we remember like V of N1 is the simplest of NFG, and the simplest of N1 is the chains in these simplices. Now we consider the map Cn, common neighborhood. Cn2 of A is containing A for every A belongs to 2 raised to V, because if you have a set, then any point of that set is adjacent to all its common neighbors. So this just means that A is contained in Cn raised to 2 of A. And similarly, we can get that A is contained in B implies that Cn of A contains Cn of B. So from this, for any A belongs to V of N1, Cn of A is either contained in V of N1 or Cn of A is equal to empty. This is because like if you apply Cn on Cn of A, we get that it is non-empty because this is Cn2 of A and A is contained in it and A is non-empty. So unless Cn of A is equal to 5, we get Cn of A is contained in N of G. This Cn map is also simplicial map because it takes chains to chains by reversing the inclusion. So it takes simplices to simplices. Now we would like this Cn to be the set to action on L of G. That is why we are like so much wondering about this map here. So we would like this thing to be the set to action on our L of G. So for this, what we need is we need that it takes L of G into L of G, and we also need it to be identity on L of G. So we have to define L of G in such a way. So we define vertex set of L of G to be the A such that Cn2 of A is equal to A. So by definition, we get that this thing is satisfied. Cn square is identity is satisfied by definition of L of G. Also, the first condition is satisfied because if B belongs to Cn of L of G, then B is equal to Cn of A for some A, such as Cn2 of A is equal to A. Applying Cn once more, we get Cn2 of B is B. And we can also see that this B belongs to N of G from this part. So basically, Cn of L of G is contained in L of G, proving that nu is a set to action. We also prove that set to action is free, because if nu of h is equal to h, then we can if nu of h is equal to h for some h in L of G, that just means that Cn of s intersection s is non-empty for that simplex s containing h. But this is false because for any simplex, the intersection here is empty. This we can prove because if this was non-empty, then there would have been AA and AJ such that Cn of AA is equal to AJ, or Cn of AJ is equal to AI, with AA is contained in AJ. But if such a thing happens, then AA is contained in AJ, which is equal to Cn of AI. Though, so since AI is non-empty, that just means that A and Cn of AI has a non-empty intersection, which is not possible. Similarly, for this case also, we can prove that it is not possible. So this will always be empty, and set to action is free. So now we proceed on to prove that L is a deformation retract of N of G. So the way we do is we consider the map Cn2 from the subdivision of N1, subdivision of N to subdivision of L. So N1 here means subdivision of N. This map we show that it is simplicial, and we can also see that F composed with I is identity. Okay, so deformation retract actually here means a strong deformation retract, not just any deformation retract. So we actually show that F is strong deformation retract So the way we show is, uh, first we show, if H belongs to H, uh, let S be the simplex in L1, in the subdivision of L containing H. Then Cn2 of S is the uh, simplex in L1 containing f of S. Now AI is contained in Cn2 of AI for any I. So that just means that all these simplices of n of g is contained in this simplex of n of g, because um, AK is contained in Cn2 of AK, all AIs are contained in AK, and all Cn2 AIs are contained in Cn2 of AK. So basically all this is contained in Cn2 of AK. We can just show that all these are contained in Cn2 of AK. So that just means that X and F of X is contained in this simplex. So what we have is, given a point X in the geometric relation of L of G, that is uh, that point X and its F of X is contained in a single simplex of N of G. Not like it's in the simplex of N of G, not in the simplex of the subdivision. So what we have is, we can just define the homotopy on that point, like on that simplex to be just a straight line homotopy. So we can do this on each of the simplices and then patch them together to get the homotopy that we need. And we can also see that this is a strong, this is deformation retract that we need. I mean, because like it takes h to f of x, and it also fits as h, capital H. So it is a strong deformation retract. Uh, okay, so now we proceed on to the second condition. L of G set 2 maps into B of G. So this is true because again, we take L1 and B1 here, the subdivisions, and we define the set F to be the map f of A is equal to A1 disjoint union sin of AK, where A here is a vertex. The vertexes here are the simplices of L of G, that is a chain of simplices of N of G. So vertices are chains, and simplices of L1 are chains of chains with respect to extension. So f of A we define as A1 disjoint union sin of AK, and this is a simplicial map, because if a chain A dash extends A, then first element of A dash is contained in that of A, and the last element of A is contained in that of A dash. So basically f of A dash is contained in f of A. So chains in extension is taken to chains in inclusion. So the simplices are taken to simplices, and it's a simplicial map. To show that f is a set to map, simplicial set to map, we just check this. Omega composed with f of A is this thing, and f composed with nu of A is, again, we can see that it is going to be this, the same thing. So basically omega composed with f is f composed with nu, and f is a set to map here. So basically we have constructed the L of G, and thus we are done with those two inequalities, this one and this one. Basically this was the only lemma that we had to prove before. So now we just go on to the last part, the Mycilsky graphs. This is an application of that inequality, previous inequality. Uh, it is also a construction that is invented to obtain triangle-free graphs with arbitrarily large chromatic number. So given a graph G, we can apply M2 on it, and then as we have seen before, chi of M2G is equal to chi of G plus 1. We can do this arbitrary number of times to get arbitrarily large graphs of arbitrarily large chromatic numbers. So we mentioned the construction. So for MR of G, we can create a MR of G. The MR of G is a graph with the vertex set R copies of B. B is the vertex set of graph G, and along with a single simplex, a single vertex disjoint from all this. So the edges here are all uh, vertices of the first copy of V is mapped into Z, I mean map connected with Z, and for other all other vertices, if UV belongs to EFG, then UI comma VI plus 1 is contained in EMR, E of MRG, and UI plus 1 VI plus 1 is also contained in E of M2G, E of MRG for every 1 greater than or equal to I greater than 1 less than or equal to I less than R. So here is an example. So if G is a graph, a graph like this, we can have a Z here and 2 copies of V of G here. This Z is mapped into the all the vertices of first copy, and this is an edge because this is an edge, this is an edge again due to the same reason, and this is also an edge. So basically this is the M2G here, and again we can apply M2 once again to get this graph here. So for any graph, okay, so as I mentioned, this thing is true, but in general MR doesn't increase the chromatic number like what M2 does. But for special cases like when G is an odd cycle, it does increase the chromatic number. So in the case of an odd cycle G, this N of G is homeomorphic to S1. After k iterations of MR, even for different R's, what we get is like the neighborhood complex will be okay, it will be Sk plus 1. That we can prove from the next theorem. But what we do is like, since neighborhood complex is Sk plus 1, from the previous inequality, we will get that chi of this thing is going to be greater than or equal to k plus 3 because Sk plus 1 here is k connected. So yeah, applying MR k times will increase the chromatic number using this. Okay, so we just mentioned that theorem, why applying MR gives us, makes the neighborhood complex from S1 to Sk plus 1. I mean, S2 increases, S1 becomes S2, S2 becomes S3 and all. So for any graph G and every R greater than or equal to 2, N of MR of G is homotopy equivalent to the suspension of N of G. So again, I just give us a rough idea of the proof. I do not formally do it completely. So we consider only the R equal to 2 case. So let N is equal to N of G and K is equal to N of M2G. So the maximal simplices of K are these three. First, there is a V cross 1 part. The first part. So this is a maximal simplex. Then there are simplices of this form where F is a maximal simplex of N. And then there is the middle part where so this looks like a cone with the base like base N. So this and this are the two N parts. This looks like a simplex. This looks like a cone in N, cone over N. And this F disjoint F, where F is a maximal simplex of N. This is the middle part. It looks like, okay, so yeah, it is again something, yeah. So basically this is the middle part. So what I do is I construct a deformation retract of K. So we can construct a deformation retract of K such that this and this are just identity on that homotopy. So it does not change anything. So this middle part, but deformation retracts to something homeomorphic to N cross 0, 1. This so basically this is a strong deformation retract on this thing. So basically this and this doesn't get affected. Again, so what we have is we have a cone on one side. The middle part is N cross 0, 1, and the other end is a whole simplex. And this whole simplex we can collapse into a single point using a Gaussian map. and there is a theorem in Matosek that mentions that this quotient map is a homotopy equivalence. So basically, what we get is one cone on one side and something homeomorphic to n cross 0 1 on the middle, and in the end the simplex is we quotient maps into a single point, so it also becomes, so basically what we get is k is homotopy equivalent to the suspension of n, because the deformation retract, applying deformation retract and quotient map gives us something homeomorphic to suspension of n. So I'm not mentioning formally what the deformation retract is, but yeah, so it's something similar to what we did before. On every simplex, we just define it by the straight line homotopy, and we patch them together to get a whole deformation, like whole complete homotopy. But I'm not doing it here. Yeah, and the theorem that we mentioned before is this: the quotient map is a homotopy equivalence. That is this. Again, I'm not giving the proof. So yeah, that's it. Yeah, thanks.
Yeah, anybody wants to ask anything? Sorry, huh? Deepak, I think I ruined some part of your talk by mentioning the words like neighborhood complex, etc.
What?
I'm saying I ruined some part of your presentation by already mentioning the words like neighborhood complex, Kineser graph, lower bound, etc.
No, no, no. It's yeah.
Yeah, anybody please ask questions, whatever. Deepak, did you go through the paper which is by Lovash? The 1978 paper?
No.
Okay, maybe you should go through that also, because that is the first time when this bound was proved, and then after that, I mean, that is the purely topological proof. And in fact, the course that we are doing right now, the
Okay.
topological combinatorics, this area of research was originated from there.
Oh.
So the interlude between topology and combinatorics, this was strongly presented through this Lovash's paper. I think title is somewhat like Kineser's conjecture, lower bound, something like that. If you want, I will share it. But मेरा बहुत edited है. Maybe I will not share that. I'll download a fresh copy and share.
Okay.
But you should
Yeah.
go through it. It's not hard at all. It is hardly 6 pages paper.
Yeah.
It's a nice read. All of you should
Hmm.
go through it.
So it's the same thing as it, or I
The
mean,
proof
it's
is
about.
little different. Yeah, it's
Okay.
about the same thing that he proves. So what he really does in that paper is that he defines another simplicial complex, and then he shows that this simplicial complex in certain restricted. So what he proves is even for a wider class, but then Kineser's graph, when you try to find the neighborhood complex of that graph, it turns out
Hmm.
to be that kind of a simplicial complex for which he proved the theorem.
Oh.
So he does that theorem in the sense of subsets, uh, it's subset system for a particular n set element, and forming some simplicial complex out of this subset system. He proves the theorem for that, and then he shows that if you try to see what is defined as a neighborhood complex for the Kineser's conjecture, it is exactly that simplicial complex. And hence, you get a lower bound
Okay.
on the chromatic number. Rather than chromatic number, I mean, all of you know that chromatic number is nothing more than dividing the vertices into color classes, right?
Yeah.
So that adjacent vertices have to go in different color classes.
Or maybe I should have mentioned the definition as well.
Oh, didn't you?
Okay, I think I just skipped over it. I didn't actually.
It's okay. Box complex is not very, but you have defined this common neighbors, etc. So just go to that slide,
Yeah.
third slide. Yeah. So actually, common neighbors is not even needed. This is much more. So given any graph and you take a vertex, all of its neighbors you collect, and all of these neighbors now form a simplex. This is how you form simplices in your neighborhood complex. So given a graph, you look at only the non-isolated vertices. Okay, you throw them in as your zero cells, and then a collection of zero cells will form a simplex if they have a common neighbor.
Okay. Yeah.
So this is
Yeah.
what a
That's.
neighborhood complex is.
Hmm.
Okay, so now if let's say you are in a Kineser graph, then given two vertices, when can they have a common neighbor? When they are disjoint from each other, right?
Yeah. Yeah.
So if let's say I have two vertices in the Kineser graph A and B, so these A and B are actually K subsets of an n element set,
Hmm.
and they having a common neighbor, let's say C, which means A is adjacent to C as well as B is adjacent to C. A adjacent to C implies that A intersection C is empty. B adjacent to C
Yeah.
implies that B intersection C is empty.
Wait. So, I mean, okay. Are you saying the common neighbor is disjoint from A or something else?
So
I did not get it.
all those subsets, all those K subsets of N,
Okay. Huh?
which are disjoint compared to one particular element,
Okay.
with respect to one particular element, they will form a simplex in the neighborhood complex of Kineser graph.
Hmm. Yeah. But okay. Yeah, but I'm still not getting how neighborhood complex is different from method representation, right? I mean,
Neighborhood complex is
okay,
a complex. Kineser graph is a graph.
okay.
So
So you are
neighborhood complex, the concept of neighborhood complex is defined for graphs. Kineser graph is a particular kind of graph. What
okay.
Lovasz did was for the neighborhood complex of the Kineser graph, but he did it in a general sense, where he proved that if at all you have a subset system which forms a
Hmm.
simplicial complex in a certain way
Hmm.
under certain conditions, then the partitioning of the vertices of this simplicial complex happens in some particular way. That is what he proves originally. And then he shows that if I'm going to construct the neighborhood complex of the Kineser graph, then this is also
Uh,
simplicial complex, right?
yeah, yeah.
So this simplicial complex has the same structure as the simplicial complex for which he proved the result. And
Oh,
hence the partition classes gives you the total number. So at least these many partitions are needed, and that's where you get the lower bound on the chromatic number of the Kineser graph.
oh, okay, okay. Yeah, I get it.
Others, did you get what I'm saying here? Maybe it's hard to understand in one go, but
So you are saying he first proved it for some specific case, and then he showed that we take the Nesser graph and then construct this neighborhood complex, and that neighborhood complex is same as the case where he proved,
no,
isn't it?
no.
No. Okay, then. Okay,
He
then I also.
he constructed a subset system.
Oh,
Okay, and for this subset system, then he constructed a simplicial complex.
Yeah.
So in a particular fashion, a subset system was defined for which a particular sort of simplicial complex was defined. Everyone here has any idea that given a graph also, there are many kind of graph complexes. Just like we have seen now box complex. There is something we also saw as neighborhood complex. There are things like clique complex, flag complex, Hom complex. Hom complex, I think, will be done by Mrinal and Sayok. So these are all graph complexes, complexes which arise from a graph. Just like that, what Lovasz did was he started with a subset system. Why
Okay.
subset system? Because they have the hereditary property. If
Yeah.
A is a subset of B and B is a subset of C, A is automatically a subset of C. And in simplices, in simplicial complex, we need this hereditary property, right?
Yeah.
Everybody remembers?
Yeah.
Sigma
Yes.
is a face of tau, and if tau is an element in the simplicial complex, we want sigma to be a face of sigma to be an element of simplicial complex. That's why we
Yeah.
need subset systems.
Yeah.
So he started with a particular kind of subset system. For that, he defined a simplicial complex, worked on that abstract simplicial complex, obtained the least number of partitions that are required for a certain condition. That is one story. Then he defined another concept called the neighborhood complex, which is defined for any graph.
Okay.
Okay. Once you have the neighborhood complex concept in picture and you know the Kineser graph, you start looking at the neighborhood complex of the Kineser graph. This is a simplicial complex in itself,
Yeah.
and this simplicial complex is a special case of the simplicial complex which he generated using the subset system.
I see.
And therefore, the number of partitions, the lower bound on the number of partitions is given. And from there, the chromatic number is bounded from below by the uh, connectivity of the neighborhood complex of this plus 3,
Yeah. This.
which
This
becomes
I get.
index plus 2 in your case because index is one higher than the connectivity as Urshit already told us in the first talk.